Hi everyone, thank you for joining the seminar. Our next speaker is Anna Helen Sisk. She is a PhD student from University of Tennessee, Knoxville. Her topic today is Epidemic Models of Violence and Network Models of Food Desert, looking at community issues through the lens of mathematical modeling. Please, Anna, you can proceed.
Hi, so first of all, I just wanted to thank you guys for putting the seminar together and for inviting me. And if you could pass my thanks along to Jimmy for recommending me, I would appreciate it. We miss him back at UT. So I'm excited to get to share some of my dissertation work with y'all today. The topic for my dissertation is looking at issues that communities face and seeing how mathematical modeling can kind of lend a hand in trying to help solve them. So we're going to be looking at two different issues today. The first one's going to look at how violence spreads in a community, and the mathematical modeling tool we're using is epidemic models of ordinary differential equations. And then the second topic we'll talk about towards the end is about food deserts, and we'll look at that through a networked models approach. Okay, so the first part of this presentation is called Linking Immunoepidemiology Principles to Violence, and it's done in collaboration with my advisor, Dr. Nina Pepperman, Dr. Judy Day, and Dr. Patricia Bamwine, who's actually an expert on the effects that violence exposure has on children. So societies have always struggled with the causes and effects of violence. Every day, more than 10 adolescents are the victims of homicide, and over 1,300 are treated for non-fatal assault-related injuries. And while the entire community has to bear the consequences of violence, they tend to disproportionately affect minority communities. Homicide is the leading cause of death in Black Americans aged 15 to 24, and the second leading cause of death for Hispanic Americans in that same age range. And while the traditional way that we approach the issue of violence is through the criminal justice system, there's recently been a new push to try to approach the issue of violence from a public health perspective. So how would you try to handle violence from a public health perspective? Well, the first step would be to think about and start treating violence like an infectious disease that can spread through a community, and then use some of your traditional disease mitigation techniques to help try to stop violence from spreading and occurring in the first place. So one organization that has really embodied this new approach of looking at violence from a public health perspective is the organization called Ceasefire, which is based in Chicago, Illinois. It is a community-led organization that's kind of taken this approach of seeing violence as a disease and then trying to treat it in their communities with these public health techniques. So a couple of the techniques that they use is contact tracing. So they'll go out and look for people who've been exposed to an act of violence. They run community awareness programs to teach their communities of how violence will affect their community and their children. And then they will also work to physically and socially distance individuals who've been exposed to violence and that are high risk of committing violence themselves. So Ceasefire has been studied by many outside organizations to look for its how effective it's been. And overall, different agencies like the Department of Justice have found it is a pretty effective way to reduce violence in the communities that it has operated in. And so thanks to Ceasefire and other like public health-based violence prevention organization, we have some empirical evidence to show that treating violence as a disease and from a public health perspective is a effective way to do violence prevention. And so this first project here wants to expand on this idea of treating violence as a disease in a public and from a public health perspective. So before we can kind of get into the mathematical modeling part of it, I need to give a little bit of background on the different fields that it encompasses, starting with epidemiological modeling. So if you're not familiar with it, we're going to go briefly into how these types of epi models work. So these models tend to break a population up into different classes. Almost all of these models will have a susceptible class and an infected class. So when we say susceptibles, we're talking about individuals who are not yet infected with the disease that you're studying, but are susceptible to infections. And the infected class are individuals who are infected with the disease that you're studying and able to transmit it to others. And then depending on what you're interested in or what disease you're looking at, you can add in a bunch of other types of classes, such as an exposed class, a recovered class, an immune class, a vaccination class, anything like that. The other aspect to these models is movement. So the individuals in these classes are able to move from class to class, depending on how they're interacting with the disease. So we can normally break down the movement that occurs in these models in two ways. We can think about it as forward movement and backwards movement. So forward movement usually happens when you interact with the disease. So you think about yourself moving forward in these classes towards the infectious class. On the other hand, to move backwards away from the infectious class, those would occur because of interactions with outside intervention. So maybe medical interaction or maybe a natural recovery rate that moves you away from the infectious class. So our epidemiological goal with this project is to formulate a conceptual, susceptible, exposed, infected epidemiological model that would work to study how violence spreads in a community. So before we can make this epidemiological model into a math model, we need to understand some important definitions from the violence literature. So these two definitions we want to look at here are adverse childhood experiences, also called ACEs for short, and protective factors. So ACEs are potentially traumatic events that occur in childhood, such as experiencing violence, abuse, or neglect, witnessing violence in the home, and having a family member attempt or die by suicide. And so these ACEs are what we consider to be interactions with the disease of violence. So these types of interactions are going to cause people to move forward closer to that infectious state for the disease of violence. And then on the flip side, protective factors are going to essentially be the exact opposite of that. These are going to be experiences and opportunities that can reduce the involvement in risky behavior in youth. So some examples of protective factors are things like economic relief, mentoring programs, therapeutic support, connectedness in family and school life, and things like that. And studies have shown that the availability of these protective factors does reduce some of the negative effects that experiencing ACEs can have, including the exposure to violence. So we would consider protective factors then to cause the backwards motion in an epidemic model. So these would be similar to the interactions with outside interventions that we'd see in traditional models, such as medical treatment and medical care. Okay. So now that we have that, we can kind of figure out where our mathematical modeling comes in. And so we're obviously going to try to create a model for this. So our goal is going to be to take that susceptible, exposed, infected epidemiological model and turn it into an ordinary differential equation model that'll look at violence spread in the community. And then we'd also want to come up with a ordinary differential equation model that could represent something like an immune system that would model how violence exposure, the effect it has on an individual with respect to the propensity to later commit violence themselves. And then once we have both of these models separately, we'd like to work to integrate the two into a multi-scale model. And these are called immunoepidemiological models. And so if that's a new modeling type for you, it's just a type of dynamical model where the within host disease processes are going to be interlinked to the population level dynamical models of disease spread. And this is kind of the goal, the mathematical goal for this project is to come up with this epidemiological model to look at disease spread on violence spread on the community level, and an immune system model to look at the effects that violence have on a person's propensity to later commit violence themselves. And just like the previous speaker, I'm going to kind of skip over a lot of the analysis because it does just pick up on the traditional epidemic modeling. So there's nothing really new there, but the interesting part here is the actual formulation of an accurate model to look at violence spread. And so we're going to be mostly focusing on the epidemic model in this presentation. So to kind of formally state our analogy between violence and infectious diseases, we will, of course, consider violence to be the infectious disease that we're studying. We're going to think about people's mental health as the immune system. We'll talk about protective factors as being like disease mitigation techniques, and then interruption and disruption techniques would be similar to your medical intervention. And the interruption and disruption techniques are those things that we saw Ceasefire using earlier. So before we actually get into the model, I'm going to go over a couple of assumptions we've made as we were building it. So first off, when we're talking about violence, we're really focusing on physical and reportable acts of violence. So that could range anything from a schoolyard fight, up to homicide. And while we recognize that there are more than just physical acts of violence, you can have emotional or verbal violence. Due to the availability of data, we will just be focusing on this type. The second assumption we made is that This model is to be used for young people or children around the ages of 14 to 17, so we're thinking high school aged, that don't have any severe underlying mental health issues where the illness could manifest as an act of violence. Okay, so now that we kind of have all that background, let's kind of dive into how we formulated this model. So here we have the diagram of the model itself. So we see that we do have a susceptible, exposed, infectious model. And so in this case, we're going to have our susceptible model is going to be the class of people who have never been exposed to violence, so a completely naive class. The infectious class is going to be the group of people who are actively committing an act of violence. And then our exposed class is, of course, going to be the group of people who have been exposed to violence. And so the difference between each of these exposed classes is going to be those in exposed 1 are going to have an exposure to violence that caused a minimal increase in their propensity to later commit violence. Those in exposed 2 are going to have an intermediate increase in their propensity to later commit violence. And then those in exposed 3, we're going to have the most severe increase in their propensity to commit violence. And then all of the arrows here in the parameters show us how we're going to have the populations moving from class to class. So now that we have this kind of theoretical idea of what we want, we went ahead and made our mathematical model out of it. So we used an ordinary differential equation model to model each of these classes. So some of the assumptions on this model is that we are working with a closed system. So if you add up all of our equations, we're going to end up with 0 on the right-hand side. Each of the interactions between our classes is going to be modeled through mass action, which makes the system very, very nonlinear. And then we make the traditional assumption of epidemic modeling that we have a homogeneous mixing of the population. All right, so we can kind of get a better understanding of how this model works. I want to look at kind of each of our parameters and where they're coming from. So we're going to start off by looking at our beta parameters. So those are these here in green. So our beta parameters are going to be responsible for all the backwards movement in this model. So going backwards away from the infectious class. And looking at beta 1 and 2, these parameters are going to rely on how effective the interruption and disruption techniques, the protective factors, and the natural healing that comes with the passage of time are. While beta 3 is going to be a little different than the other betas, parameters, it's going to look at, it's going to behave more as an automatic removal rate from the infectious class. So people who are, after a person is done committing an act of violence, they're going to be automatically bumped back to that third exposed class. The next set of parameters we're going to look at here are the omega parameters. So those are these guys in red. And so these are going to be responsible for most of the forward movement we see in the model. So we want these parameters to kind of encompass a couple different characteristics. So the first one is we'd like the omegas to look at the quality of your exposure to violence. So what we mean by quality is, were you the victim of violence? Was it someone in your close personal network, or was it maybe just an act of violence committed in your community? Another thing we take into account is how robust a person's mental health is to an exposure of violence. So for example, if you maybe have a really strong support system at home or at school, then perhaps an exposure to violence isn't going to have much of an impact as if, for say, you did not have that type of support system. And then this is obviously a place where the individual component of the system is kind of coming into play. So in the future, this is where that individual level of the immune system model would come. And then one last note on these omega parameters that move us from the exposed classes is that in this model, not all exposures to violence are going to move an individual to the next exposed class. It's only going to be the exposures to violence that have a significant enough impact on that person's mental health to increase their propensity to later commit violence. And our last set of parameters we're going to look at today is the mu parameters. So those are these guys in blue. And they're responsible for the rest of the forward movement in our model. And they're going to be very similar in assumptions to our omega parameters. The big difference here is that the mu parameters are really just looking at how the initial exposure to violence impacts a person's propensity to commit violence later in their life. So that's really kind of the whole background to the model. And so I wanted to talk us through now a couple of numerical simulations. So one thing I want to note before we jump into those is that these are just like example simulations or toy simulations, as we haven't incorporated any real world data to them yet. And so these are more just to get a feel for how the model works, if it's working how we expect it, and then what type of results we could expect once we do incorporate data to them. Okay, so the first set of parameters we're going to look at are here. So we're going to start off looking here on the left. So here we have a, this is going to be considered our base case parameter set. So this is going to be kind of the set of parameters that we're always going back to and just adjusting 1 or 2 parameters here and there for the rest of the simulations. So we're starting off with the assumption that we're working, that we're modeling a community that has a very, very low level of preventive measures, violence prevention measures. And we can see that when you have a low level of violence prevention measures, you're going to have a high level of violence in the community. And so our infectious class here is this purple line. So obviously it's up really high, like above 80%. So while that's not a realistic number, the trend that a low level of violence prevention means you're going to have a high level of violence in your community is kind of what we were looking for out of these simulations. On a similar note here on the simulation to the right, we wanted to see what would happen if we would increase the propensity for violence after exposure. So you have a community that's very, very susceptible to the impacts that a violence exposure has. Mathematically, that's looking at ramping up those omega values or those forward movement parameters. And when we do that, we see what we would expect, which is an increase in the amount of violence occurring in the community. Again, the actual value is not really what we're looking for. It's not realistic, but that idea that it has increased when you increase that forward movement or that propensity for violence in a community. So this is kind of like one end of the extreme where we have lots and lots and lots of violence occurring in this community. And so on the other end, we wanted to see what could happen if we could kind of force violence to die out in a community. And we were able to do that in 2 different ways. So this orangish line here represents the exposed one. And so what we're able to do is to essentially force the entire population to the first exposed class. So the first way we did that was by looking at increasing violence prevention. So either stopping violence from happening in the first place or protecting the people in the community from the effects that violence exposure would have. So mathematically, that looked like decreasing our omega parameters in half. And we ended up putting everyone, our purple line kind of goes to 0 and everyone ends up here in the orange line. To get this same effect, kind of going through a different route, we were able, we looked at what would happen if you were to increase the amount of support available to a community after a violence exposure. So in other words, what happens if we were to kind of increase the backward movement in that model, so increasing those beta values. And so to get this similar effect that we got from the figure on the left, we had to increase the beta values 5-fold. So to get this behavior here, we only had to decrease the omega values in half. But to get that same behavior here, we had to increase that by 5-fold. So a result from this that could be useful for community leaders would be that investing in violence prevention measures is going to be a lot more effective than investing in support after exposure. And then the last numerical simulations I wanted to talk about today was what happens if we had a parameter change during our run. So this could represent maybe how a community deals with violence or approaches violence over a longer time period. And so starting here with our simulation on the left, we see we're starting off with a community that has a pretty high level of prevention measures in their community. But at some point here, around time equals 17, we see that those prevention measures, for whatever reasons, are going to be drastically decreased. And so once that happens, we see for a little bit after that decrease, the positive effects that these prevention measures have kind of stick around for a little bit. But as time goes on, we end up having this like dramatic reversal back to essentially what looks like our base case scenario. So we end up with a really high level of violence occurring in the population. On the other hand, the simulation on the right looked at kind of the opposite scenario. So what happens if you start off with a community that has lots of violence, very low prevention measures, but then introduce those later on? And when we see this introduction happens, the amount of violence in the community does drop off, but it starts to level off at still a relatively high rate. We don't see that dramatic reversal that we saw in this figure over here. It does level, it goes down, but it doesn't completely switch like we saw in the other simulation. And so the conclusion we can draw from that is that the negative effects that violence exposure has on a community is going to have a much greater impact in the community than the positive effects that the preventative measures have. And so what a community leader could do with this result is, hopefully realize that prevention measures need to be introduced to a community early and consistently to maximize their effects. And so just a couple kind of conclusions off of this first project is that even though we're looking at toy examples and example numerical simulations, they do help show that a model like this can provide useful strategies on the most effective way to handle violence in a community, and that these types of results our model could offer is going to be very important to those who are actually working in the field, like social workers, to determine where their effort is most important and most effective, especially since these types of organizations tend to have limited amounts of funding. And finally, besides people who are working in the field, this type of results are going to be helpful for policymakers and community advocates so they can best deal with violence in their community. So that's kind of the end of this first project, and I'll go ahead and move into the second one, and you guys can ask questions at the end. So the second project that I'm working on is called Can Public Transportation Networks Help End Urban Food Deserts? And this work is, again, in collaboration with my advisor, Dr. Nina Pfefferman, and then with Dr. Kristen Rapazzo from the EPA. Okay, so what is a food desert, if that's a topic you're not familiar with? So according to the USDA, a food desert is defined as a census tract that is both low income and low access. And by low income, we mean a poverty rate of 20% or greater, or a median family income at or below 80% of the statewide median family income. And low access means that at least 33% of a population in a census tract lives more than 1 mile away from a supermarket or large grocery store in an urban area. And so why do we care about this issue? Why is this something that's being studied? So people who live in food deserts tend to have a higher rate of facing food insecurity, which just talks about if people know where their next meal is coming from, if they have a secure access to getting food when needed. And this is food insecurity tends to have a major negative effect on children. The next reason is that just like the issue with violence, it tends to disproportionately affect our minority communities and other communities that are already disadvantaged. And from a public health perspective, food deserts can lend to a lot of major public health issues. So they tend to have a role in causing diet-related illnesses like obesity, diabetes, high blood pressure, and high cholesterol for people living in food deserts. So the question I wanted to tackle with this project is how can city leaders work to eradicate food deserts? And that's obviously a really broad topic, so I wanted to narrow it down by looking at the role that public transportation could play in this. So how I was going to do this was to create a network model where my food deserts and grocery stores were going to represent the nodes of the model, and any type of public transportation route would be the edges to the network model. And so to kind of build one of these, I decided to look at a part of northern Milwaukee County in Wisconsin, and was able to gather the data needed to make this model from some ArcGIS hubs, the USDA, and Google Maps. So before we build up our model here, a couple of assumptions that we made during this is that we used Google Maps to calculate routes and travel time between food deserts and grocery stores. And we ignored any variability that occurred with these travel times that could be caused by traffic, weather, construction, time of day, time of year, and so on. Okay, so let's go ahead and build up this network model. So this is the part of Wisconsin that we're looking at in this black outline. And so we see here that our blue shaded areas are going to represent our low income census tracts. Our green shaded areas are going to represent low access census tracts. And these red shaded areas are going to be the food desert. So remember, those are both low income and low access. And what I did here was I picked a representative apartment complex in each of the food deserts to represent one of the nodes, to represent the node for that food desert, so that we're able to calculate travel times. So then the next step is to add in our grocery stores, which are represented by these orange boxes. So now we've essentially have all of our nodes for the network model plotted. And finally, the last step is to add in the edges to the model. And so those are represented by these purple lines, which are the public transportation routes in this part of Milwaukee. In Milwaukee, their public transportation system completely relies on busing. Okay, so then this is our full network model here, and we're going to look at some analysis on it next. So to kind of get our feet wet in this, I wanted to look at how long does it take to get from a food desert to its closest grocery store using public transportation. And we see on the high end here, we have 35 minutes, and on the low end, we have somewhere around 10-ish minutes, and then we have them kind of scattered in between that. And so something that's important here is that these times aren't just, you get on the bus outside of the apartment, you get off the bus right in front of the grocery store, you're on the bus the whole time. Often these travel times include a lot of walking to the bus stop and then walking to the grocery store and back. And so, for example, this first one here is 22 minutes of walking time and only 13 minutes of bus time. And so our goal then would be to try to reduce the travel time that it takes to get from a food desert to a grocery store, especially focusing on the ones that have a high travel time. So how do we kind of analyze our network models here? We're going to use centrality measures, and centrality measures are just a way to identify which node is going to be the most important to the network. And so today we're going to look at two types of centrality measures. We're going to look at a closeness centrality and a betweenness centrality. So you can calculate the closeness centrality by just, for each node, computing 1 over the sum of the distance from one node to all the other nodes. And here, the lower the closeness is, the more important that node is to a network. So it's going to be closer to all of its neighboring nodes. And then the second betweenness centrality we're going to look at is, the second centrality measure we're going to look at is the betweenness centrality. And so the betweenness centrality looks at the number of times a node is on the shortest path that connects to the two other nodes. And so in this case, the higher betweenness score means that that node is the most important because it's the most central into getting to all the different places in your network. Okay, so we started off by calculating our closest centrality from all of our grocery stores, which are here, to each of the food deserts. And so we see on the low end, it takes on average about 35 minutes to get from these 3 grocery stores to any of the food deserts. And on the high end, we're looking at over an hour. So by looking at your closeness centrality for a network model like this, your goal would be to try to figure out a way to decrease this average closeness. And a way a city leader could do this would be to try to incentivize grocery stores to open in an area where it would have an average lower closeness than what we currently see. This is a little bit more realistic than asking for a grocery store to be built in each of the food deserts, as that's often something that companies are not willing to do. The other thing you could do is examine bus routes to see if, maybe small changes or modifications could be made to them that will allow for an average lower closeness. And for this example in particular in Milwaukee, I know they're currently working on revamping their busing system, so maybe that's something they could take into account. And then the next centrality measure we're going to look at is the betweenness centrality. And I was actually more interested in looking at the betweenness of the edges instead of the betweenness of the nodes. So in order to do that, we just look at the dual of the network. So when looking at the betweenness of the edges, all we're asking is which edge or which bus line in this case is used the most often to connect each of the food deserts to each of the grocery stores. And so when we looked at this, we saw that there was 3 bus lines or 3 edges here that really stood out, which was the blue in the 63 had a betweenness score of 29, and then the 76 line had the highest betweenness score of 43. And so we see here that the 76 is a very important bus line in connecting food deserts to grocery stores. And so the betweenness centrality is something that really needs to be considered when a city is thinking about altering any of its bus routes, especially those with a high betweenness. So altering the 76 could greatly impact people who live in food deserts' access to grocery stores. Something to help relieve some of this pressure on your high betweenness centrality lines would be to try to offer comparable alternatives to these high betweenness lines. So if you have a delay on one of these lines, it won't drastically affect a person's travel time to a grocery store. And then kind of one of the things I found the most interesting about our betweenness centrality is that it's different than the other ones. So I did calculate other centrality scores that I just didn't share for the sake of time today. But most of the other centrality measures, you can look at them and find out ways to make improvements. So how can we help improve access to grocery stores? But the betweenness centrality really focuses on how do we not make it worse? How can we make sure that we keep food deserts at least where they're at and they don't get any worse? And sometimes when working on problems that have to do with politics and city leaders and things like that, this is sometimes the best we can hope for. So I found this centrality measure to be kind of important in that sense. So this is a project I'm actively working on during this summer. And so kind of what I'm working on right now is to incorporate the updated census data and grocery store data for making these models. I also am working on moving all of the analysis over to ArcGIS, so there's no dependence on Google Maps. And then I'm also going to look at a bunch of different places around the country of varying size, so maybe more suburban areas to very urban areas, and look at kind of how these centrality measures, how these changed looking around the country. And so I just wanted to, thank my lab and my advisors for their help. They let me give a practice talk and gave me some feedback on this, and I'd be happy to take any questions.
Thank you, Anna, for the talk.
Thank you.